Dear students, after studying this module, you shall be able to know about surfactant and their behavior in the solution. Learn about the composition of surfactant and the role of their different part in imparting solubility in different phases. Classify the surfactants on the basis of the charge on their polar head group, and finally know about the various applications of surfactants in different fields. In our daily life, we use a wide variety of consumer products such as shampoos, detergents, conditioners, toothpaste, cosmetics, etc. But have you ever thought, what are they composed of? The answer to this is they are composed of surfactants. Surfactants are also widely used in the following industries: emulsions, paints, adhesives, etc. Let us begin with understanding what are surfactants. The term surfactant is a blend of surface active agents, which literally means active at surface. Surfactants are compounds that lower the surface tension or interfacial tension by their tendency to get adsorbed at surface and interfaces. Interface is a boundary between any two immiscible phases, and the term surface is used when one of the phase is a gas, usually air. Let us see some examples of surface and interface. Solid vapor, we have surface. Solid liquid, we have interface. Solid is another interface. Liquid vapor is also a surface. Liquid interface. The driving force for the adsorption of surfactant at an interface is its lower Gibbs free energy at the phase boundary. The interfacial free energy per unit area is the amount of work required to expand the interface and is usually termed as interfacial tension. Thus, the surface tension of water is equivalent to the interfacial free energy per unit area of the boundary between water and the air above it. When that boundary is covered by surfactant molecules, the surface tension is reduced, as you can see in the figure shown here. Denser the surfactant pack at the interface, greater will be the reduction in surface tension. Surfactant may absorb all types of surfaces and interfaces given above. Generally, we have interfaces which have water as the liquid phase. Some examples of the different interfaces and products are as shown in the table. Examples of interface: involving a liquid phase. We have solid liquid, it is a suspension, and the example is sand and water. Again, liquid and liquid, we have the type of system is emulsion, and the example is milk or cream. Liquid vapor interface, the type of system involves a foam, and the example includes a shaving cream. As we have seen, the fundamental property of a surfactant is the tendency to accumulate at interface. The surfactant concentration at a boundary depends on the surfactant structure and also on the nature of the two phases that meet at the interface. Therefore, there is no universally good surfactant suitable for all uses. The choice depends on the application. A good surfactant should have low solubility in the bulk phases. Some surfactants are only soluble at the oil-water interface. Such compounds are difficult to handle but are very efficient in reducing the interfacial tension. Let us now understand the composition and structure of surfactants. Surfactants are amphiphilic. The word amphiphile, first introduced by G.S. Harley, is derived from the Greek word amphi, which means both. Surfactants are usually amphiphilic organic compounds that contain two parts, one which is soluble in a specific fluid, the lyophilic part, and the one which is insoluble, the lyophobic part. In case of water as a fluid, the water soluble part is called hydrophilic and water insoluble part is called hydrophobic. So, you can see in the figure, the hydrophilic part is referred to as the head group and the hydrophobic part as the tail. The hydrophobic part is usually linear or branched chain of 8 to 18 carbons, which can be aliphatic, aromatic or a mixture of both. The sources of hydrophobic part are generally natural fats and oils, petroleum fractions, relatively short synthetic polymers or relatively high molecular weight synthetic alcohols. The degree of chain branching, the position of the polar group and the length of the chain are parameters of importance for the physico-chemical properties of the surfactant. The polar part of the surfactant may be ionic or non-ionic, which give the primary classification to the surfactant. The choice of polar group, relative size of the hydrophobic and polar groups is decisive in determining the properties and physico-chemical behavior of a surfactant in water. A surfactant usually contains only one polar group. Recently, there has been considerable research interest in certain dimeric surfactants containing two hydrophobic tails and two head groups linked together with a short spacer. These species are termed as Gemini surfactants or double chain surfactant. They show several interesting physico-chemical properties such as very high efficiency in lowering surface tension. A typical Gemini surfactant is shown in the figure, as you can all see. Now we are going to understand natural surfactants. Nature's own surfactants are usually referred to as polar lipids. These are abundant in all living organisms. In biological systems, the surface active agents play the same role as surfactants in technical systems to overcome solubility products as emulsifiers, as dispersants, to modify surfaces, etc. Some examples of this in biological systems are bile salts are extremely efficient solubilizers of hydrophobic components in the blood, while mixtures of phospholipids pack in ordered bilayers of the surfactant liquid crystal type, and such structures constitute the membranes of cells. One of the important examples of a phospholipid is lecithin. It is extracted from phospholipid rich sources such as soya bean and egg. Now we will understand about the dynamics of surfactants in solution. One characteristic feature of surfactant is their tendency to diffuse in water and adsorb at interfaces between air and water or at the interface between oil and water. The water insoluble hydrophobic group may extend out of the bulk water phase into the air or into the oil phase, while the water soluble head group remains in the water phase. This alignment of surfactants at the surface modifies the surface properties of water at the water air or water oil interface. Another fundamental property of surfactants is that monomers in solution tend to form aggregates called micelles. Micelle formation or micellization is an alternative mechanism to adsorption at the interfaces for removing hydrophobic groups from contact with water, thereby reducing the free energy of the system, and it is an important phenomena since surfactant molecules behave very differently when present in micelles than as free monomers in solution. Only surfactant monomers contribute to surface and interfacial tension lowering, and dynamic phenomena such as wetting and foaming are governed by concentration of free monomers in solution. The micelles may be seen as a reservoir for surfactant monomers. The exchange rate of a surfactant molecule between Michel and bulk solutions may vary by many orders of magnitude depending on the size and structure of the surfactant. As you can see in this figure, we have a surface and we have Michel there, and the diagram also shows what is happening in the bulk. This is the dynamics of the surfactant in solution. In Michel, the surfactant hydrophobic group is directed towards the interior of the cluster, as you can see in that picture, and the polar head group is directed towards the solvent. The Michel therefore is a polar aggregate of high water solubility and without much surface activity. When a surfactant adsorbs from aqueous solution at a hydrophobic surface, it normally orients itself, its hydrophobic group towards the surface and exposes its polar group to the water. The surface becomes hydrophilic, and as one can see, as a result, the interfacial tension between the surface and water is reduced. Adsorption at hydrophilic surface often results in more complicated surfactant assemblies. Let us understand how surfactants are classified. A primary classification of surfactant is made on the basis of the charge of the polar head group. If the charge is negative, the surfactant is called anionic. If the charge is positive, it is called cationic. If a surfactant contains a head with two oppositely charged groups, it is termed zwitterionic. So, we can divide surfactants into the classes anionic, cationic, nonionic and zwitterionic. As you can see in the table, we have surfactants showing 4 groups: anionic, cationic, nonionic, zwitterionic. And here the diagram shows how the head is there. In the first one you can see there is no ion, next comes the negative and then comes the positive, and then we have a zwitterion showing both negative and positive at the head and while the tail is free. Let us talk about the next part, that is various types of surfactants one by one. Let us begin with anionic surfactants. Anionic surfactants contain anionic functional groups at their head, such as sulfate, sulfonate, phosphate and carboxylate. Anionic surfactants are used in greater volume than any other surfactant class, as they are used in most detergent formulations, and the best detergency is obtained by alkyl and alkyl aryl chains in the C12 to C18 range. Soaps, which are the largest single type of surfactant, are anionic surfactants. It is produced by saponification of natural oils and fats. Soap is a generic name representing the alkali metal salt of a carboxylic acid derived from animal fats or vegetable oils. Soap bars are usually based on mixtures of fatty acids obtained from tallow, coconut and palm oil. Over the last 50 years, soaps have been replaced with more efficient substances like alkyl sulfates, alkyl sulfonates and alkyl benzene sulfonates. Anionic surfactants are sensitive to water hardness. The counter-ions most commonly used are sodium, potassium, ammonium, calcium and various protonated alkyl amines. Sodium and potassium impart water solubility, whereas calcium and magnesium promote oil solubility. Amine, alkanol amine salts give products with both oil and water solubility. Let us see some examples of alkyl sulfates. The examples are ammonium lauryl sulfate, and another example is sodium lauryl sulfate, also called SDS. Another classification is alkyl ether sulfates, and under this heading we have sodium laureth sulfate and sodium myreth sulfate. The third classification is sulfonate. Under this we have perfluorobutane sulfonate and dioctyl sodium sulfosuccinate perfluorooctane sulfonate, also known as PFOS. Next is cationic surfactants. For this category, the hydrophilic part is positively charged. As I have told you earlier, this group has no wash activity effect, but fastens to the surfaces where they might provide softening, antistatic, soil repellent and antibacterial or corrosion inhibitory effects. The most typical applications are their use as softeners, fabric softeners and antistatic. The counter-ion of cationic surfactants is usually a halide or a methyl sulfate. pH dependent primary, secondary or tertiary amines have become positively charged pH greater than 10. Let us note down some common examples of cationic surfactants. They are with the permanently charged quaternary ammonium cation. Number 1, hexadecyl trimethyl ammonium bromide. Number 2, cetyl pyridinium chloride, which is also called as CPC. Another one, benzethonium chloride, written as BZT. We also have 5-bromo 5-nitro 1,3-dioxane dimethyl dioctadecyl ammonium chloride. Another example, cetriammonium bromide dioctadecyl dimethyl ammonium bromide. Another example, citryl trimethyl ammonium bromide. Next one, cetyl trimethyl ammonium chloride. This is written as CTAC. And the last one, we have benzyl alkonium chloride, which is known as BAC as the short form. Coming to the third classification, that is non-ionic surfactants. A non-ionic surfactant has an uncharged hydrophilic part. These substances are well suited for cleaning purposes and are not sensitive to water hardness. They have a wide applications among cleaning detergents and include groups like fatty alcohol, polyglycosides, alcohol, ethoxylates, etc. Many long chain alcohols exhibit some surfactant properties. Prominent among these are the fatty alcohols, cetyl alcohol, stearyl alcohol, and oleal alcohol. Some common examples of non-ionic surfactants are glucoside alkyl ethers. Among these, we have decyl glycosides, lauryl glycoside, octyl glycosides. Another example can be seen by glyceryl laurate. Let's talk about the Zwitter ionic surfactants. Zwitter ionic surfactants contain two charge groups of different sign. Zwitter ionics are often referred to as amphoterics, but the terms are not identical. An amphoteric surfactant is one that changes from net cationic while Zwitter ionic to net anionic on going from low to high pH. Neither the acid nor the base site is permanently charged. That is, the compound is only Zwitter ionic over a certain pH range. At the isoelectric point, the physico-chemical behavior often resembles that of non-ionic surfactants. Below and above the isoelectric point, there is a gradual shift towards the cationic and anionic character respectively. Zwitter ionic as a group are characterized by having excellent dermatological properties. They also exhibit low eye and skin irritation. Therefore, these are well suited for use in shampoos and other personal care, that is cosmetic products. Zwitter ionic amphoteric surfactants have both cationic and anionic centers attached to the same molecule. The cationic part is based on primary, secondary or tertiary amines or quaternary ammonium cations. The anionic part can be more variable and include sulfonates as in chaps. Other anionic groups are sultanes. Sultanes are the inner sulfonic acid salt of a strong inorganic acid and are commonly referred to as sulfobetanes. They are similar to betanes, which are inner carboxylic acid salts of a weak organic acid. Both molecules are considered Zwitter ionic at neutral pH, where the nitrogen on the hydrophobic tail is cationic. The polar head groups are anionic and add to the hydrophilic properties of the molecule. Because the quaternary nitrogen is always positive, these molecules cannot obtain anionic nature at any pH and are not truly amphoteric, although they are commonly referred to as such. Common types of Zwitter ionic surfactants are N-alkyl derivatives of simple amino acids such as glycine, betaine and aminopropionic acid. Betanes, even phosphates such as lecithin. So far we have learnt about the classifications of surfactants, and as we learnt, we have 4 types: positive, negative both and non-ionic. Let us now learn, it is time for the applications of surfactants. Surfactants play an important role as cleaning, wetting, dispersing, emulsifying, foaming and anti-foaming agents in many practical applications and products. Products include a wide variety of consumer products as seen. We have shampoos. You are all familiar with various types of shampoos you use every day. We also have dish detergents. All maids use them, such as Vim, etc., etc. Even the laundry needs detergents. They are also surfactants. We also have conditioners. Fabric softeners are another new name which we are familiar with. Diapers also use surfactants. Even your contact lens cleaners have some type of surfactant. Cosmetics is another example. Toothpaste, various types, they all contain some bit of surfactant, and surfactants are also widely used in various industries. We have paint industry, we have emulsions, we have adhesives, even de-inking of recycled papers in flotation, washing and enzymatic processes. All these industries use surfactants in large quantities. We also have heavy tertiary oil recovery industry, ore flotation, dry cleaning, pesticide and herbicide applications, water repellency, even the waxes such as ski waxes, snowboard wax use surfactants of various types, quantum dot coatings, even pipelines, liquid drag reducing agent, and finally inks of various types along with laxatives. They all contain surfactants of some category or the other. Now we will summarize what we have learned in this module. Number 1, surfactants are surface active agents. Number 2, they may act as detergent, wetting agents, emulsifiers, foaming agents and dispersants due to their tendency to adsorb at surface and interfaces. Thirdly, they are composed of two groups, hydrophilic, water loving, and hydrophobic, that is water hating. The presence of both the groups imparts some solubility in polar as well as non-polar environment. Another thing, along with the adsorption at the interface or the surface of the liquid, they also form aggregate in the bulk phase called micelle at higher concentration. We also learnt about primary classification of surfactants, which can be done on the basis of charges present on the polar head groups as anionic, cationic, non-ionic and zwitterionic. Surfactants have many applications in household and commercial field, which is increasing day by day, and I hope you have understood all that.